All right, hi everyone, how's it going? My name is Sean Lewis, I'm one of your TAs, and we're going to be going over recitation week 4 problems today. So this week is mostly talking about forces here, and we'll get into some of the more complicated versions of some force problems, as well as one or two rotational motion problems. So it'll be a good review, especially before your midterm coming up pretty soon. So first problem here, problem 5.7a, we've got an object hanging from the ceiling with 3 chords being present there. So we've got chord A, B, and C. And it's asked us to find the tension in each. And so really with any force problem, the first thing to do always is to recognize that we need to start drawing a free body diagram. That's going to be super important in order to solve all these problems. So thing is, though, I mean, we may have seen free body diagrams before in lecture and last week recitation. The thing that's a little bit tricky about a problem like this is that typically when we are drawing out a free body diagram, we'll draw like the main object of the picture and draw the forces on that object. However, in this problem, that's not really what we're interested in. Instead, the point of interest that we want to be drawing is this right here, this intersection point between the 3 chords that are in question here. So let me draw that real quick. Let me do a free body diagram here. So we've got that tension B, or that chord B, going off to the side like that, tension B, or I'm just going to label it for tension B. We've got chord A going off this way, so the tension A is going to be going off that way too. And then tension C is going to be going straight down, tension C. So that's my free body diagram. Again, I'm just drawing that intersection point of those 3 chords. And then sort of next thing I want to do, or for most of these force problems, a good way to start thinking is how can I split this problem up into components? Generally, for us to find things out about the problem, the different forces that are involved, splitting it up into its different components is a good way to generate 2 different equations that we can then start meshing together and solving for some values. So let me do that. I'll say for the x component stuff, let's look at that first. So let's look at tension B. How do I find the x component of tension B? A couple of ways I could do that. Number one, I could say, well, the x component of tension B is going to be like this value right here, right? It's going to be the x component of tension B. And I can recognize that based on the picture, they tell me that this angle here is 45 degrees. And then I think, was it congruent angles or some mathematical law here says that this angle is also 45 degrees. Or I could recognize that this vector right here could also be considered the x component of tension B. A couple ways to do this, but ultimately what I'm seeing is that in order to isolate out that horizontal component of tension B, of the force tension B, I need to multiply the magnitude of tension B times cosine of 45 degrees. Same sort of thought process can be done for tension A, getting the x component of tension A. That's going to be tension A times cosine of 30 degrees. And the only thing really to pay attention there is that the x component of tension A that we're looking at, tension A going like this, is going to be pointing off in the negative x direction. So I have to include that minus sign there for the vector. Then to finish out this equation, recognize that because this object or because this thing that we're looking at is not accelerating or not moving side to side horizontally in any way, then the acceleration here must be 0. And so we know that sum up all the forces, sum of the forces is equal to mass times acceleration. If acceleration is 0, then this right side of the equation is 0. And so that is our first equation that we're going to be working with for this problem. I can do the same thing, but for the y component pieces, which go through step by step for tension B. Recognize that the y component of tension B, I can get that value in a couple different ways. I mean, I can represent it. I'm just representing it here on the graph, this y component of tension B in red here a couple times, but just recognizing that I can isolate out the vertical component of tension B by multiplying the magnitude of tension B times sine of 45 degrees. And the same sort of thinking for tension A. Tension A times sine of 30 degrees. So recognizing that I can get this vertical piece of tension A because this angle is 30 degrees here, etc., etc. Hopefully you're feeling pretty comfortable about isolating out components like this. For vectors is something that I definitely should be comfortable with pretty soon. And so recognizing that this tension A, the vertical component, the y component here is positive, so I have to do a plus sign. And then finally, there's one last force that it has vertical components that is present here, and that's tension C. And so tension C is there too. The only thing is it's going downwards into the negative y direction, so you minus tension C. And all of that's equal to 0 because there's no acceleration up or down either. Okay, so let's try to solve this. Couple things to note. First, the way that this problem is worded is a little bit strange. Really what it's trying to ask, or what it wants to ask for, is find the tensions, tension A, B, and C, in terms of W being the weight of this object. And so really here I can recognize that I have 3 unknowns. I got tension A I don't know, tension B, and tension C. But real quick, I can just make the note that because tension C is only attached to this object in question, then I can say outright that tension C is just equal to the weight of the object. Hopefully that's clear why that's the case, but the weight of the object is just a force going down like this, and that's connected straight up to our cable or our cord C. So tension C is just equal to W. So we already know that value, which means the only values we don't know are tension A and tension B. So tension A, tension B are the things that we're trying to solve for. And so we have 2 unknowns and we got 2 equations, which is perfect. So just system of equations, we can solve this for tensions A and tension B. And that's exactly what I'm going to do. So to start solving this equation, we've got two equations here, 2 unknowns, so I have to start solving this system of equations. The way I'm going to start doing that is I'm going to take my x component equation and modify and manipulate it a little bit. So I'm going to manipulate the x component equation. And what I'm going to do is I'm going to solve for tension A. So I'm just going to rearrange some things, ultimately solve, let's say that tension A, or I'll say negative tension A times cosine of 30 degrees equals negative tension B cosine 45. All I've done there is I've moved the tension B piece over to the right-hand side of the equation, and then a couple more steps just to solve for tension A. Tension A is equal to tension B cosine 45 degrees divided by cosine 30 degrees. So what this allows me to do is then take this value for tension A that I just found, this expression for tension A, and plug it into my y component equation. So that's the next step, is substitute into y component equation. And so let me write this out real quick. So I still got that tension B sine of 45 degrees there from my y component equation. And then I have plus tension A, but I'm substituting in that value. So I've got tension B cosine 45 degrees divided by cosine 30 degrees. So that was my tension A. Now I'm just substituting in this new expression for it. That sine of 30 degrees is still there. and then minus tension C, but I'm just going to replace it with the value that we know that tension C is, which is W. Remember, we decided that's what tension C was. And all of this is still equal to 0. So then I'm going to do some quick math here and show you, and just sort of trust me on this, we're going to do a little bit of algebra. I'm going to skip those steps though and say that tension B is equal to, a few things get mushed together, so like sine of 30 over cosine 30 becomes tangent of 30, and some things get moved around a bit. But so trust me that we get to this point. Check on your own if you're unsure. But we do get to this point where we have tension B is equal to, and on the denominator we have tangent of 30, cosine of 45, plus sine 45, all this over W, or sorry, W all over this expression. And this comes out, if I type this into my calculator, this comes out to be 0.9 W. So 0.9 W is our value for tension B. So that's our solution of tension B. Then to solve for tension A, all I need to do is take my original manipulated version of the x component equation and substitute in my my new value for tension B. So do that real quick. Tension A equals, I'm plugging in 0.9 W for tension, the value for tension B, and cosine 45 is still there, cosine 30 is still there, and so all this equals 0.73 times W. And that's my value for tension A. So answer this problem, tension C we said was equal to W, tension B is equal to 0.9 W, and tension A 0.73 W. Okay, problem 5.7b, very, very similar to what we have going on, or what we had going on in the previous problem. Same sort of deal here, same thing. We have to recognize that our point of interest is this intersection point of the three chords that are in question here. And so I'm going to draw that free body diagram real quick right here and say that tension B is going off this way, like this, TB, and tension C, which I'm just going to, same reasoning as before, I'm just going to call it W because it's connected to the object that has some weight. Tension A is going off this way, and I'm going to mark down some things here, like the fact that tension B makes an angle of 45 degrees with the ceiling there, and tension A makes an angle of 60 degrees right there with the wall. Okay, ultimately though, even though the problems are shifted a little bit compared to the last one, the tensions are going off in different directions, it doesn't really matter. What matters is that we approach the problem in the same way. And so I'm going to write out this problem in terms of the x components and the y components of the forces that are in question. So first, x components. I'll write this down. So let's look at tension B first. I think exactly the same as the previous problem. So I can see that to get out the horizontal piece of tension B, I just need to multiply the magnitude of the vector by cosine of 45 degrees. Then for tension A, maybe less obvious how we get the horizontal component of vector A. That's going to be something like this. And it's, if you look at it enough, hopefully you recognize by now how to isolate out these components. But it's, the side opposite to the 60-degree angle, so it's going to be the magnitude of tension A times sine of 60 degrees. And because it's going to the left, because it's going in the negative direction, I got to put the minus sign there. No other horizontal components in this problem, so all of this is equal to mass times acceleration, right? Because this is ultimately still just the sum of the forces equals mass times acceleration, but this object is not accelerating in the horizontal direction, so the acceleration is 0. So that's my x components. Y components I'll do over here. Y components. same deal, same thought process here for tension B. So tension B, isolate out the horizontal, or sorry, the vertical piece of tension B. It's going to be sine of 45 degrees. For tension A, recognize that the vertical piece of tension A is going to be going downwards this time, so it's minus sign there, minus tension A times cosine of 60 degrees. And we've got tension C, or in this case I already labeled it, I already know that it's just W. It's going down, so it's going to have that minus sign, all that equal to 0. Okay, so same deal as before, two equations, two unknowns, TA and TB, and so we need to solve that. We need to start combining these together. So I'll do that same way as before. I'm going to solve for tension A out of the x component equation and substitute it into the y component equation. So that's the first thing here. I'm going to solve for tension A right from the x component equation. So it's going to be TA is equal to tension B times cosine of 45 degrees divided by sine of 60 degrees. So some quick algebra there just to isolate out tension A. And then next step, just like before, we're going to substitute that in to our equation for the y components. And I'm just going to rewrite out that equation after I do that substitution. So I've got TB sine of 45 still, that's still there, minus, now I've got tension B times cosine of 45. Right, this is now what our TA value has become. And then we're going to have cosine of 60 degrees divided by sine of 60 degrees, which is just our cotangent of 45 degrees. So I did a little bit of simplification there. Hopefully that's clear how that happened. But just all I did there, substitute in tension A into our second equation here. I got our minus W still there, and all that's equal to 0 still. Next step, just solve for tension B. Solve for tension B. So we're getting our one variable out of this equation, actually getting a value for it. So again, I'm going to kind of skip all the algebra here. That just trust me or check on your own that this does in fact happen. If we isolate out tension B, I got sine of 45 on the denominator minus cosine of 45 degrees cotangent of 60 degrees. All of that underneath W, and this comes out to a value of 3.3 W. Okay, so then to solve for tension A, it's a real quick step from there. We're just going to plug in tension B back into our equation for TA. So plug in, and then this becomes tension A is equal to value of tension B is 3.3 W times cosine 45 divided by sine 60. And plugging that into our calculator, all that comes out to be 2.7 W. So total answer for this, tension C is easy enough. That was something we assumed at the beginning. That's just equal to W. Tension A is equal to 2.7 W, and tension B is equal to 3.3 W. All right, next problem. Problem 5.25. I'll read it out real quick and sort of think about how you'd approach this while I'm reading it, but I'll go through my thought process for this problem shortly. So this problem says that we have a worker who's pushing a box with a mass of 16.8 kilograms on a horizontal surface with a constant speed of 3.5 meters per second. The coefficient of kinetic friction between the box and the surface is 0.2. And we want to figure out, A, what is the horizontal force the worker must apply to maintain the motion, which the motion here they said was the constant speed that I mentioned before. And then part B, if the force calculated from part A is removed, how far does the box slide before coming to rest? Okay, so let's take this one step at a time. We'll focus on part A first. something about a force being applied to this box to maintain constant speed. So first thing we want to do, I just drew out a picture here. This is generally what I like to do. If you're in my recitations, you've heard me say this before. I like drawing out a general picture of just what the problem text says, so I don't have to keep rereading a paragraph over and over again just to figure out whatever next piece of information I need. But so this is just the general picture. But first, really important thing we need to do for any of these force problems is draw our free body diagram. So that's the first step always. Draw a free body diagram. And that means I have to label all the forces involved here. So obviously this box has mass, which means it has to have some weight to it. So weight is just mass times gravity. mg going down, of course, gravity pulls down. And then we have the normal force going straight up. And then we have the force that the worker is applying to the box. I'm just going to say that they're pushing it to the right. So that's the force that the worker is applying. And then there's, obviously, just based on the problem text, there's friction involved. It's a surface that has some friction to it. And so there's going to be a friction force, which by definition opposes the direction of motion. Not necessarily the direction in which the force is applied, but the direction of motion of the box. So in this case, I'm assuming that, I'm just going to actually label up here, the velocity of this box is to the right as well, so the direction that the worker is pushing it in. So because our velocity is to the right, I'm going to say that the force of friction is pointed backwards. So F, little f, is force of friction. Okay, so first step, what horizontal force, what force F does the worker have to apply in order to maintain this motion, this velocity of 3.5 meters per second? So to actually do this, I am going to need to apply really the one and only equation that we have to solve force equations, and that's the sum of all the forces is equal to mass times acceleration, where acceleration is the rate of acceleration for whatever mass we're talking about. What's important, really important to notice in how this problem is worded is that, at least for part A, we have a mass, a box that has constant motion, or it is in constant motion. It's moving at 3.5 meters per second, which means if it's constant, it is not accelerating. So it's a really important thing to recognize here is that our acceleration in this problem is 0, at least for part A here. We'll deal with part B in a sec. But part A, acceleration 0, which means that if I write out my equation, sum of all the forces in the direction of motion in the x direction, that's going to equal 0. So let me write this equation out. Sum of all the forces, F is one of the forces going off in the positive direction, so leaving it positive, and then another force going in the negative direction is the force of friction, so minus the force of friction. And then all of that is equal to mass times acceleration, but of course we just said that acceleration is 0, so it equals 0. So in this case, solving for, again, this is part A here, the force F is just equal to the force of friction. Easy enough, except the only problem is I don't really know outright what force of friction is, so I have to be a little bit more careful here. I can define the force of friction as the coefficient of kinetic friction. And just so everyone's on the same page, this symbol here is mu, mu. Greek letter is just a cursive U, basically. But it's the coefficient of kinetic friction. It's just a number, it has no units to it, times the normal force. So force of friction is coefficient of kinetic friction times the normal force. Great. Okay. We're kind of stuck again, though, because I don't know what the normal force is for this box. But there's a way I can find it out. And the way that I think about it is because the normal force is, the way I think of it, as sort of a reaction force to the object being in contact with the surface, I can do the same process of summing all the forces in the y direction this time and setting that equal to mass times acceleration in the y direction, which of course in this problem, because the box isn't moving up or down, this acceleration is 0. So sum up all the forces in the y direction and set it equal to 0. If I do that, I've got the normal force pointing up, I've got mg, the force of gravity or the weight, pointing down, equals 0. And so here the normal force is equal to mg. So let me plug that into my equation here. Again, I'm just sort of defining more and more specifically what the force of friction is. So before it was just force of friction, now it's the coefficient of kinetic friction times the normal force, and now it's the coefficient of kinetic friction times my new definition for the normal force, mg. So I can start plugging in these numbers. So the force being applied by the worker is just 0.2 times, which 0.2 is the coefficient of kinetic friction, times the mass of the box, 16.8 kilograms, times gravity, which is 9.8 meters per second squared. And this all comes out to 32.9 newtons. So that is the force that our worker must be applying in order to maintain the constant velocity of 3.5 meters per second. Okay, let's do part B. Let's do it over here. Part B, I'll read it again. It says that if this force that we just calculated, 32.9 newtons, is removed from the box, how far does the box slide before coming to a rest? So you can imagine, like, this worker's pushing the box, and then they just let it go for a second. It's going to slide a little bit further, slowing down, obviously because there's friction involved, but eventually it'll come to a complete stop. So how do I figure out what that is? Well, since we've removed a force, we're kind of dealing with a slightly different problem here. So I'm going to redraw my free body diagram here. Still got the normal force going up, still got mg going down. The velocity, at least initially, is still going off to the right, which means the force of friction is still opposing that motion. Force of friction, block still has mass, but now there's no force F present anymore. And now I can say that, once again, the only equation we really have available, sum of all the forces, I'll stick with the direction of motion, so if sum of all the forces in the x direction is equal to mass times acceleration in the x direction. And now, because this problem is different and because the problem is talking about how the box is slowing down means there must be some acceleration present. And so I'm not going to say that the acceleration is 0 in this case. It has to be some other number. And that's what we're ultimately going to need to solve this problem. So let me write out this equation here. Sum of all the forces in the x direction, all I have there is the force of friction. And that's still equal to mass times acceleration. I gotta be careful though, because force of friction is going off in the negative x direction, so I put a minus sign there. I can take the force of friction though and write it in from the previous part of our problem, part A, and say that the force of friction is equal to the coefficient of kinetic friction times mass times gravity. It's equal to still mass times acceleration in the x direction. And I can start then solving for the acceleration. And the reason why I recognize the acceleration as being important, one is the only thing I don't know in this equation, so it seems like it's going to be important. But also that if I know what the acceleration of this block is, then I can figure out something about how far it's gone. If I know how much it's slowing down, I can figure out with kinematics how far it's gone. So just rearranging this, acceleration in the x direction is equal to the coefficient of kinetic friction times gravity. And so the acceleration is, and sorry, actually there's a minus sign here that I forgot, but acceleration is minus 1.96 meters per second squared. Okay, so then at this point, now that I have acceleration, I also know how fast this block was going initially. Right? Initially, it was going just like how I was describing in part A. It was going at 3.5 meters per second. I also know that its final velocity is going to be 0 meters per second because the problem says it came to a rest at the end of part B here. So I know its initial velocity, its final velocity. I want to find some delta x. I want to find how far it's gone, and I know acceleration. That's telling me kinematics. We got to use some kinematics here. So I'm going to use the kinematic equation Vf squared equals Vi squared plus 2a delta x, because this is something that has all the pieces that I need. I can solve for delta x there. And so ultimately I find that delta x is equal to, I'm just going to rearrange it real quick, do some quick algebra, initial velocity squared over 2 times the acceleration. And so once again, that's 3.5 meters per second squared over 2 times the acceleration. Oh, sorry, there's another minus sign out in front here. I forgot about that. Sorry, negative 1.96 meters per second squared. Just like that. And so my delta x is equal to 3.13 meters. All right, let's keep going. So this next problem, number 31, again, I'll read through the problem, kind of start thinking about how you'd approach it. I'm going to detail the way that I do it. But so in this problem, we have someone who's either pushing or pulling, depending on which part of the problem we're on, a box with a mass of 10 kilograms that is moving along an inclined plane or a ramp that is angled at 55 degrees above the horizontal. There's also a coefficient of kinetic friction between the box and the ramp of 0.3. And we want to calculate the magnitude of the acceleration of the box if you're pushing on the box with a constant force of 120 newtons. And that force is being applied parallel to the ramp surface. And then for 2 different situations. And the first one we're going to deal with is if that force is being directed down the ramp. So essentially you're pushing the box down the ramp. So draw out a picture here of just very basics of what that looks like and some important information that the problem told us about. But again, so as always, we've got to have our free body diagram first. That's going to really help us out here. And so the way that I do things for problems like this, maybe not everyone does it like this, but it's just the way that really makes sense to me. Instead of having to deal with like the force being applied down at this diagonal angle and everything like that, I'm going to take that box and rotate it so that now it's facing entirely horizontally, just like it would be if it was on a horizontal ground. So that force now is just pointing off to the left, which means that if I were to draw on this picture the normal force, it would have been going off diagonally like that a little bit, this normal force here. But now it's going straight up and down like this. And the force of friction is opposing the direction of motion. Direction of motion would just be like down the ramp that way. That's the velocity, which in this rotated perspective is to the left, which means that the force of friction is going off to the right. Force of friction. And then the final piece is the weight of this box, ng, which normally would be going straight down just like that. But in this rotated picture, so because I took the box and I've rotated everything, now instead of going straight down, it's going off to the side like this. And it's going off to the side at an angle. In that angle, you can check this with some geometry if you want. But this angle is that same 55 degrees that the ramp is inclined at. So this is our free body diagram. Of course, it still has the mass in there too. But yeah, so this is what we're working with. This is what we're going to build all of our equations off of. So let's start doing that. As always with our force equations, or force problems rather, we have one equation available to us, F equals ma, which in this case, really what I'm interested in, I'm going to write out the equation for the sum of the forces in the x direction, being equal to the acceleration in the x direction. Of course, acceleration is ultimately what we're going to want to be solving for, but let me write out the different forces that we have going on here. So firstly, we've got our force F that we are applying to the box, which I know is 120 newtons, but I'm going to leave it just as a variable for a second. Force F, what's important though is that it's going off to the left. And even though it's something like the force that we're applying, doesn't matter, it's negative because it's going off to the left. Then we have force of friction, which is going off to the right. And even though we sort of sometimes think of force of friction as being like, an adversarial force, is like fighting against what we're trying to do, it doesn't matter. It doesn't matter like if it's, what it is, or it doesn't determine whether it's negative or not. All that matters is what direction the force of friction is pointing in. So in this case, it's pointing in the positive direction to the right, and so it's positive here in our equation. And then finally, there's the last piece of the puzzle, which is the horizontal component of this mg vector. So we can't forget about that. At first, I recognize that it's pointing off in the negative direction, it's pointing off to the left. And then to isolate out that it's just another vector problem. So maybe I'll write it out a little bigger over here on the right side of the screen so you can see it perhaps a little bit better. I've got the mg, I've got the 55-degree angle right there, and then this horizontal piece, or horizontal component rather, just like that. And so just like any other vector, all of this is the horizontal piece. It's the magnitude of the vector, in this case mg, times whatever trig function allows us to isolate out that horizontal piece. So in this case, it's going to be sine of 55 degrees. And that's all of the forces that we have going in the x direction. And so all this is going to be equal to mass times acceleration. So before I can start solving for acceleration, I need to do one more thing, or a few more things. I need to figure out what this force of friction is. And so I'm going to write this whole equation out, but with some clarifying pieces. Instead of just saying force of friction in general, I'm going to say that it's actually the coefficient of kinetic friction times the normal force, which is true. The rest of the equation stays the same for now. Sine 55 equals ma. But I don't know what the normal force is in this problem. But that's okay, because I can actually solve it for this. I'm going to do it over here real quick. I'm going to say, in order to solve the normal force, I do sum of all the forces in the y direction is equal to mass times acceleration in the y direction. When I'm looking at this, this free body diagram here, though, we know that the box is not going to be accelerating up or down in this picture here. So acceleration in the y direction is 0 in this case. And so sum up all the forces in the y direction. I've got the normal force going up in the positive direction, so that's positive n. And then in the downward direction, I've got mass times gravity, but only a component of it, right? Only a piece of mg is going in the downward direction. So the way I isolate out that vertical piece is I take the cosine of 55 degrees, and that's equal to 0. And so the normal force is equal to mg cosine 55. Perfect. So I then can plug this into my equation here. So let me write it out one more time. Got that minus f still, plus the coefficient of kinetic friction times mg cosine of 55 degrees minus mg sine of 55 degrees. And all of that's equal to ma. Then I can do some algebra. I can just plug in my numbers. I know what the force F is, 120 newtons. I know what the coefficient of kinetic friction is, it's 0.3. I know the mass, it's 10 kilograms. I know gravity. I know everything else here. And so I can just solve for the acceleration A. I'm going to skip writing out that algebra. Just try it on your own. Make sure you get here. But this comes out to be a negative 18.34 meters per second squared. So that's our acceleration for pushing this box down the ramp. Then for part B, let's have a little more space here. For part B, slightly different problem, my same basic setup, but we're going to be pushing that 120 newtons up the ramp instead of down, and pushing the whole box up the ramp as well. So I'm going to redraw my free body diagram because our forces have changed. So things have been reoriented. So I'm going to make sure I draw my picture again just so I know exactly what's going on. So there's my mass m. Normal force is still going up. Mg is just going to be going off to the side still like this, or diagonally off. angled at that 55 degrees, just like before. And then the only thing that's different now, though, is that the force that we're applying, force F, is going to be going off to the right. It's our direction of motion going off that way too, our velocity. And then because that's the case, because we're pushing the box up the ramp, pushing in the other direction, then the force of friction always opposes that motion. And so that is going off to the left this time. So let me write out my equation again, same thing as before, sum up all of the forces in the x direction, set that equal to mass times acceleration. And so here I've got 120 newtons, positive this time because it's going off in the positive x direction. I've got minus the force of friction, minus because it's going off to the left. Force of friction, because the problem hasn't fundamentally changed except for the orientation of my vectors, orientation of my forces, I know that the force of friction is going to be described by the same thing as we did from part A. So I'm just taking this piece. The coefficient of kinetic friction times mass times gravity times cosine of 55 degrees. And then minus the horizontal component of the force of gravity, which is still pointing in the same negative direction as before, and it's the same value. And so it's the same thing from part A. Then minus mg sine of 55 degrees equals mass times acceleration. And so all these numbers in here, all the variables here, I know the values for them. And so I can solve really quick for acceleration. Again, I'm going to skip the algebra for this, but you can start to prove to yourself that that's true. And so the acceleration comes out to be a positive 2.3 meters per second squared. So those are my two answers. For part A, we got a negative acceleration, which makes sense because we're pushing the box down the ramp in the negative x direction. So we got a negative acceleration. And then a positive 2.3 meters per second squared for part B, going off in the positive direction. Okay, next problem, problem 33. So here we have two boxes stacked on top of each other, and we're pulling a rope that's attached to the bottom one, the only one of them. And we are pulling these boxes along a ramp. We don't know what the angle of the ramp is yet, but we're told that we're pulling them at a constant speed of 15 centimeters per second. And that the coefficient of kinetic friction between the ramp and the box is, the ramp in the lower box is 0.444, and the coefficient of static friction between the two boxes is 0.8. I want to know, first part A, what force do we need in order to exert in order to accomplish this? I won't worry about part B for a second, but the first thing to sort of keep in mind is we don't necessarily want to worry about what's going on between the two boxes just yet. All I really care about here is what we are doing to this system, in this case pulling on it with a rope, and what we want the system to do, which in this case is maintain a constant speed of 15 centimeters per second. So how do we do that? I don't really care about what the internals of the system are doing, what the two boxes are doing, but I care about the whole thing. So let me draw out my free body diagram here. So first, like I said, I don't care about what's going on with the individual boxes. So I'm just going to say, I'm going to combine them together into like one big mass, one big M, which is just going to be, of course, the two masses added together. But I'm just going to do that. So I don't care about what the individual pieces are. I care about the whole thing. I've got the force that I'm applying to it with the rope going off that way, mass times gravity going off diagonally. Again, I'm doing the same thing as the previous problem of just sort of turning the situation a bit so that everything's horizontal here. That mass times gravity is going off at some angle. I don't know what the angle is yet though, but it corresponds to this angle of the ramp up there. And then I have the force of friction, which is going to be opposing the direction of motion. And I have the normal force that's going up. Okay, so I got all this stuff here. First thing that I want to do, I want to figure out what that angle is just so I get that out of the way so I don't have to worry about what the value is too much. It's actually really straightforward, but it's something that we have to investigate this picture a little bit for in order to actually discover what that is. So even though they don't tell us what the angle is, they tell us what the lengths of the sides of this ramp are. And so I can say that just from basic geometry, or actually, sorry, trig, I can say that the angle theta is equal to the inverse tangent of the vertical piece over the horizontal piece. So that's 2.5. Hopefully you can see that okay. Divided by the horizontal piece, 4.75. And so just doing that math real quick, this comes out to be 27.8 degrees. So real quick, just want to get that out of the way to establish that. So actually, I'll write that right here. Theta equals 27.8 degrees. In this case, the mass big M is going to be equal to the two boxes added together, 48 plus 32, which is 80. And just so my reference, for my reference, so I can deal with that later. And then so let's actually solve part A here and say that I know I have to deal with the equation F equals ma, specifically talking about forces in the x direction, acceleration in the x direction, recognizing that because the problem says that the box or the system, the two boxes, are going to be moving with a constant speed of 15 centimeters per second. Constant speed means no acceleration. That means acceleration is 0, and sum of the forces in the x direction equals 0. So if I write this out, sum of the forces, I've got force F going off in the positive direction, so that's positive there. I've got then the force of friction going off to the left in the negative direction, so that's negative. And then the horizontal piece of mg, so it's going to be mg cosine, or excuse me, sorry, that's mg sine of the angle that we just decided, which mg sine of the angle that we just decided, which was 27.8. I'll plug that in a second. All that equals 0. So now we can start explaining or like defining a little bit more of what this force of friction is. So force of friction, we know from the previous problem, that's just mass times acceleration. Restart. Okay. So next thing we want to do is write this out a bit more. So we've got the force F still there. Force of friction, just remember from last part of the problem, the way or how that eventually boiled down is the exact same way as it does here. It ends up being coefficient of kinetic friction times the normal force, which we can identify as being mass times gravity. Actually, mass times gravity times cosine of the angle theta, like 0. And I'm going to do something a little bit here. I just want to make this extra clear. These masses that we're talking about are not just any mass, that's talking about the total mass big M. That's what we've been talking about this whole time. So I just want to make that clear so we know what we're subbing in. Oops, and I forgot my my horizontal piece of gravity, so that's in there too. Minus big M times G sine of theta equals 0. Okay, now we're good to go. All of this is known. We know what big M is. We know what the angle is. We know what coefficient of kinetic friction is. So I can solve for the force F. This ends up being force F equals 57.8 newtons. Awesome. So we're applying force of 57.8 newtons. That's it. So for part B, though, it wants to know what is the magnitude and direction of the friction force on the upper box. So this has to do with the contact, the place of contact between the upper box and the lower box. So we then have to start caring about what that coefficient of static friction is between the two boxes, which they tell us is the 0.8 value right here. So let me draw this out real quick for part B. Part B here. So part B, I'm just going to draw a quick free body diagram of my upper box. So here the mass is the 32 kilograms. We got the normal force. We got mg. There's no force directly being applied to it, but there is a force of friction that's going to be opposing the direction of travel. So essentially this box is trying to slide off the back of this top, the bottom box there. Only thing that's different is that it's static friction, so it hasn't started moving yet. So to think about this properly, let's look back at the question. They're asking us to find the magnitude and direction of the friction force on the upper box. So we already have the direction down. Now we just need the magnitude. So in order to get that, all I do is my usual sum of the forces in the x direction is equal to mass times acceleration in the x direction. Of course, in this case, the acceleration taking place here is none because our top box isn't moving. So this becomes 0. And so I add up all my forces on the left-hand side of the equation here. I've got force of friction going in the negative x direction, and I've got mg times the sine of the angle theta. I know it's negative because it's pointing that way, and this is just from the previous logic for what the component, x component of the force of gravity is. All this equals 0. And so the force of friction equals negative mg sine theta. And so here, all I need is to plug in my values for m, which we know is just the smaller box. That's 32 kilograms. Gravity is 9.8 meters per second squared. And then sine, the angle is, what did we say? We said 27.8 degrees. And this is our force of friction. And so force of friction becomes 146 newtons. All right, next problem, problem 47. So here we have a small car that has a mass m that's traveling at a constant speed around the inside of a track that is going in a vertical circle. So basically it's doing like a constant loop-de-loop over and over again. The circle has a radius of 5 meters, and the normal force that is exerted by the track on the car at the bottom of the track, point A, is equal to, and this is a little bit confusing, it was confusing to me, but what this value is here, the normal force is equal to 2.5 times the mass of the car times gravity. So that's not milligrams or anything. So 2.5 times the mass of the car times gravity. And we want to know how much time does it take the car to complete one revolution around the track. So this might be kind of weird because in the past problems, like they haven't really asked us anything about time or like any timing, anything that has to deal with forces, and it may not be super obvious how we get going with this, and we got like a circle happening, but regardless, we can approach this problem in the same way as we were the previous ones by first starting out with our free body diagram. And so I'll draw a car like this. It's got a weight, and so it's got mg going straight down. It's got a normal force going straight up, and that's pretty much it. That's all that's really happening right now. So let me write out my equation. It seems like the only thing I can really do is sum up all the equations in the y direction is equal to the mass of the object times the acceleration of the y direction. Okay, so seems pretty straightforward here. Now, though, is the really important part. For circular motion, the acceleration of an object that is going in a circle is not the same as that linear acceleration that we were dealing with the previous problem its radial acceleration, which its definition is the velocity of the object squared, the velocity that's going around the circle, divided by the radius of the circle. So really important to recognize that because we have an object going in a circle this time, we have to think about acceleration as the radial acceleration. So let me write out our F equals ma equation though. I've got the normal force going up, so it's positive. I've got mg going down, so it's negative, and that equals mass times acceleration, but acceleration is v squared over r this time because it's circular motion. So what can I do with this? I'm looking at my equation here. It tells me a value for mg, or sorry, for the normal force. Let me plug that in real quick. So 2.5 times mg minus mg equals mv squared over r. And so simplifying this, 2.5 times something minus 1.0 times the same thing becomes 1.5 times mg equals mass times v squared over r. And so then I can cancel out the masses on both sides. And it seems like to me the only thing I don't know here in this equation is the velocity, right? I know what the radius is, it's 5.0 meters. I know what g is, obviously. And so I'm just going to solve for the velocity here. It's the only thing I can really solve for. Velocity becomes, we find out, is 8.6 meters per second. Okay, so I know how fast the car is going around the circle, but it wanted me to find how much time does it take the car to complete one revolution. So I haven't really done that yet, but if I recognize all I need to know in order to figure out how much time it takes for something going 8.6 meters per second to go around the whole circle is I just need to figure out how far does the thing have to go in order to travel the entire circle. I need to know what the circumference of this track is. So ultimately what I'm trying to do is say that time is equal to the distance traveled divided by velocity. Really simple equation. But this distance here, in this case, is going to be the circumference of the circle. And so that's going to be 2 pi times r. So plugging that in real quick, the time that it takes to travel the entire circle or one revolution around the circle is going to be 2 pi r divided by the velocity, which is, we just said, 8.6 meters per second. So I plug in my value for r, and I get the time is equal to 3.7 seconds. And I'll be a little bit more specific here, and instead of saying lowercase t, I'll say capital T, because when we're talking about something going around in a circle and how much time it takes to go once around the circle, then it's specifically talking about the period. So period is how much time it takes to complete one revolution. All right, second to last problem. We have problem 74. So getting a little bit more complicated here. We got two blocks this time, mass 1 and mass 2. Mass 1 is 20 kilograms. They're on a ramp, or mass 1's on a ramp that's angled at 53.1 degrees. And the coefficient of kinetic friction between mass 1 and the ramp is 0.4. We want to know what the mass of M2 is, the one that's hanging off the edge there, if it descends 12 meters in the first 3 seconds after the system on both blocks have been released from rest. So a little bit more complicated here. I'm just going to label some things. So I'm going to say that at some point up here is where the M2 started and descended 12 meters. It took some time of 3 seconds to do that. We've got mu k, that's the coefficient of kinetic friction, that's 0.4 right there. I've got the angle alpha of 53.1 degrees. M1 is 20 kilograms. So I'm just throwing some things in there just so I see that happening in the picture. So yeah, how do I approach this? How do I start figuring out ultimately what mass M2 is? My general advice for problems like this, if you're in my recitation, you've heard me talk about this before, that if we are able to identify a way to isolate out some property of the system that can describe the individual components of the system, that's really, really good. That's something that we want to try to do. And so in this case, my first thought is, if I am able to figure out how much one of these blocks is accelerating, or what the acceleration is of one of these blocks, that automatically defines the acceleration of the other block, right? Because these two things are stuck together by this rope. So if one's accelerating at 10 meters per second, the other one has to be also accelerating at 10 meters per second squared, because if it wasn't, then the rope would break and the problem wouldn't exist anymore. So that's really the first sub question I come up with is, what is the acceleration, or how do I find acceleration? And so the first thing I recognize is that, well, it doesn't tell me a whole lot about M1, but it tells me something about M2 moving a distance in some time after starting from rest. And so actually I'm going to label that in the picture too. I'm going to say up here, V initial equals 0 meters per second. So I've got V initial, I've got time, I've got some delta x. That's telling me kinematics is going to be useful here. And I look at my equation for the kinematic equations, and I see that there's an equation there of delta y is equal to the velocity initial in the y direction plus 1/2 acceleration in the y direction times t squared. So looking at the information here, again, this is all for block M2. Actually, I'll say that right here. That's ultimately the side block M2. So I'm finding the acceleration of the entire system based on the block M2 information. So velocity initial, 0, because it starts from rest. Time, 3 seconds, delta y, 12 meters. I'm going to rearrange this a little bit, solve here, and find that the acceleration in the y direction of block M2 comes out to be negative 2.67 meters per second squared. Or I'm sorry, actually that's going to be, that's positive, my bad. Okay, so we got our acceleration of M1. Our acceleration of M2. That's really good, because that means that I can take that information, I can take that value and apply it to the entire system and every individual piece of the system, which means that block M1 must be accelerating at 2.67 meters per second squared. So let me take that information and draw out a free body diagram of M1. I'm going to do it over here. So next we're going to draw, it says draw free body diagram of M1. And so I'll do that real quick, like this, there, M1, got the normal force going up. We got the tension of the rope going that way. We've got mg going down here. And double checking, do we have friction in this situation? Yes, we do. And it's going to oppose the direction of motion, just like that. So let's write, or you got this situation. This seems pretty good. If I'm thinking about how, ultimately what I want to solve in this problem, which is the mass M2. So let me do that actually over here too. I'm going to draw a free body diagram of M2 as well. This M2, all we've got is the tension going up, and we've got mg going down. That's it. So real quick, actually, I want to write out an equation for mass 2 just to show, explain why we're going to be solving stuff for M1. So if I write out some of the forces in the y direction is equal to mass times, and this is mass 2, right? We're talking about block 2 here, times acceleration of block 2. If I write this out a bit, only forces that are present are tension, got mg going down, again, that's mass 2, is equal to mass 2 times acceleration. So it seems like I can solve for M2 here. In fact, I'll do that real quick. If I we'll use tension is equal to M2 times A plus G. So I just brought it over, factored out M2, and so mass 2 is equal to the tension of the rope divided by acceleration plus gravity. So it seems like I'm really close to finding what the mass M2 is, but I don't know what the tension of the rope is. So that says, all right, like I'm almost there, but I got more work to do. I got to think about M1. So M1 over here, I have to write out my equation for sum of the forces, or the sum of the forces, adding up all the forces in the x direction for M1. So I'll do that real quick. Sum of the forces in the x direction is equal to the mass 1, right? Because we're talking about mass 1 here, times the acceleration. So all the forces in the x direction, I've got tension T going off to the right. I've got the force of friction going in the opposite direction, or not even the opposite, but just, well, it is the opposite, but also more importantly in the negative direction. And then also the component of mg. So mg, the horizontal piece of that, which is going to be sine of the angle alpha, which we know what it is, but I'm just leaving it as a variable for a second. And all of that is equal to m1 times acceleration. So remember, the thing we're trying to solve for is the tension. So I'm going to rearrange this a little bit, or continue solving for the tension here. I've got tension is equal to m1 times the acceleration plus m1 times g sine of alpha plus force of friction. So almost there, but I need to be a little bit more specific about what the force of friction is. So I'm just going to rewrite this, a m1g sine alpha plus force of friction here. Remember from the previous problems, the way we go about solving for the force of friction is ultimately by looking at our free body diagram for m1 here, doing the sum of the forces in the y direction being equal to 0. And so I've got actually a couple things. Maybe actually, let me back up a little bit. What we're trying to do for the force of friction, we need to find the normal force, right? That's one of our requirements, because we know that the force of friction is equal to coefficient of kinetic friction times normal force. How do we get the normal force? Then we do this equation here. Sum of the forces in the y direction equals 0. So I've got the normal force minus mg cosine of alpha equals 0. And so the normal force equals mg cosine of alpha. So then we take that, plug it into my force of friction, and plug that back into our tension equation here. So I've got tension equals m1 times the acceleration, which again, remember, we know what that acceleration is. It has to be the 2.67 meters per second from before, right? Because that applied to the entire system, plus m1 times g sine of alpha, plus force of friction now has become mu k, the coefficient of kinetic friction, times mg, that's m1g cosine alpha. Hopefully you can see that. I hope that didn't run off the page too much. But ultimately this comes out to be a tension of, we're just going to plug in all the values. All the values for m1, which you know are 20 kilograms, value for g, alpha, we know it's 53.1 degrees. Everything in there, we know what all those numbers are. It comes out to be 257 newtons for tension. Great, so now that we have tension, we can finally plug that into our M2 equation. And so we find that M2 is, right, and we're just remember one more time that we know what the acceleration is because we know the acceleration of the whole system, know what g is, and so we plug this in and we get 36.0 kilograms. Now, final problem. Let's get this done. So we have a book that has a mass of 5 kilograms placed against a vertical wall. You apply a constant force F to the book, where F is 96 newtons, and the force is being applied at an angle 60 degrees above the horizontal, as we see in the picture there. the coefficient of kinetic friction between the book and the wall is 0.3. If the book is initially at rest, what is its speed after it's traveled 0.4 meters up the wall? So some motion is going to be happening here. The book's going to start here and it's going to go up to here, that 0.4 meters. We've got that coefficient of kinetic friction is 0.3. This force F is 96 newtons. I'm just labeling some things in here from the problem. 5 kilograms to get my mind in the right place there. Labeling this out, but then, of course, more importantly, drawing our free body diagram here. So here's the book again. It's got some mass, so it's got mg going straight down. It's got the force F coming in right there, coming in at an angle of 60 degrees. I'll label that 60 right there. Right, that's the 60 degrees. And then the force of friction is going to be opposing the direction of motion of the book. So I've already assumed that this book is going to be moving upwards, right? So the force of friction has to oppose that. It's going to be acting on the book and going downwards like that. So how do I find out its final speed, its final velocity after it's traveled some distance? Immediately alarm bells going off telling me I'm going to have to be doing kinematics, right? If it's talking about distances and I know that there's some velocities involved, and obviously I assume there's going to be some acceleration happening. That's telling me kinematic stuff is involved for this problem. So that's where I'm going to end up. But to get there, I know I'm going to have to deal with sum of the forces equals mass times acceleration again, because we always do. And actually, I forgot one force here, and that is my normal force, which recall that the normal force is a reactive force to something being in contact with a surface. So in this case, that surface is the vertical wall, and so the normal force is going to be going off to the right like that. So what I'm going to do first is I'm going to write out my sum of the forces in the y direction is equal to the mass of the book times acceleration in the y direction, because I know that that's the direction that motion is going to be happening, so I know it's going to be important to write that out. And ultimately, that's the acceleration I'm going to be interested in. So I know acceleration is happening there. I'll write out the forces that are going on. I know that the force F is going upwards in the positive y direction, but only part of it, only a piece of it. And it looks like that's going to be, let's see, I want the vertical piece of this force, and so I'm going to have sine of 60 degrees. I've got the force of friction going down, so it's minus the force of friction. And I've also got mg going down, so that's a minus mg. All that equals to mass of the book times acceleration in the y direction, just to be sure. So, can write this out a bit more. Before I write a bit more, the only thing I don't really know is the force of friction. So let me write out down here, force of friction. How do I get that? So how do we get this force of friction? So I'm thinking, I know that the force of friction is defined as the coefficient of kinetic friction times the normal force. And I know that I can find the normal force by doing sum of the forces. In this case, it's in the x direction, right? So it's going to be the stuff that's going side to side here. So sum of the force in the x direction is equal to the mass of the book times the acceleration in the x direction. There's no acceleration in the x direction, though. It's not moving side to side, so equal to 0. And so if I write this out, adding up all the forces in the x direction, I've got the normal force going off to the positive x, and I've got some component of, or the horizontal component of f cosine 60 degrees, which is going off to, in the negative x direction, all that equals 0. And so here the normal force equals force times cosine 60 degrees. Awesome. So I know the normal force. I can plug it into my force of friction equation and into my big equation here. F sine of 60 degrees minus force of friction becomes coefficient of kinetic friction times the normal force, which is force F times cosine 60 degrees minus mg is still there, equals ma in the y direction. And I can rearrange this a bit and ultimately solve for acceleration. So I'm going to skip that math just because I'm running out of space here a little bit. And I'm just kind of trust me on this. We know all these values. We know what force F is. We know what the coefficient of kinetic friction is. We know what gravity is. We know what the mass is. So all of this comes out to be, do some algebra, 3.9 meters per second squared. Then we can finally answer the full question, which is what is the book's final speed if it started from rest? If its initial velocity vi was 0 meters per second and it traveled 0.4 meters and now we know its acceleration is 3.9. How do we find its final velocity? We're going to use that kinematic equation that we saw before. V final squared is equal to vi squared plus 2a, and then change in displacements, in this case delta y. Initial velocity is 0, so that goes away. Final velocity is equal to the square root of 2a delta y, which I can plug in my values. 2 times acceleration, we just said was 3.9, times delta y is 0.4. And so all of this comes out to be our final velocity is 1.8 meters per second. Awesome. And that's it. We solved the problem. Perfect. And that was the last problem for this recitation. So hopefully that was all clear. If not, ask myself or email myself or come to my office hours Friday 1 to 3 p.m. every week for this quarter, or talk to your whichever TA you attend for recitation, and we'll gladly help for any of these problems.